Alright, this video is going to be about thermodynamics, and there may be some things in this video that are kind of hard to understand or grasp, but just try to stick with it, and I hope that you will be able to understand at least kind of the surface layer of what we're talking about. But thermodynamics is, in a nutshell, thermodynamics is the study of heat. Sometimes it's also called using heat to do work or moving heat, and that particular definition I think you'll understand more about in just a moment as I go on. There's two laws of thermodynamics, and you see them shortly here. I'm going to go ahead and jump in to talk about the first one. The first law of thermodynamics is something that you should already know. That's just the law of conservation of energy, which states that energy cannot be created or destroyed, but it can change forms. In other words, energy has to go somewhere. Energy will flow from one place to another, and we've learned kind of about energy changes already, but that's the point. Energy can change form, but it's got to go somewhere. In this part, you have to know the definition of a system, and that's simply a group of atoms or a collection of objects that have internal energy, which is symbolized in our case by the letter U. The internal energy of a system can be changed in one of two ways. The first way is easy to think about. You can either add heat or you can remove heat from a system. Obviously, if you heat something up, you cool something down, that's going to change the internal energy of a system. And a system can be anything meets the definition of a system. The table that you're sitting in front of, the chair you're on, yourself, your pencil, anything is a system, and you can add heat or remove heat from that system. You can heat it up and cool it down. That'll change the internal energy. Another way to change the internal energy is to do work. Now, work can be done in two ways. Just like heat can be added or removed, work can be done by the system or it can be done to the system. If we say work is done by the system, a good example of that would be a person that is walking up a flight of stairs. Right? If you walk up a flight of stairs to go to the top, it's not too hard to see that the energy you had to start off with inside of yourself, because you are the system in this case, compared to the energy that you had to end up with, those are not the same, because you definitely had more energy to start with than you did when you ended up with. You used some of that energy to walk up the stairs, and the energy came from inside of you, from inside of the system, and that energy ultimately flowed out of you in order to get some work done. Okay, and you got some work done, you went up the stairs. An even better example would be running a mile around a track. When you do that, it's a lot easier in that case to see that you definitely have less energy at the end than you did at the beginning, because you used your own energy. Energy came from within the system, you used it to do some work to get around the track, and energy flows out of you, mostly in the form of heat. You get really hot usually when you're working hard like that, and that heat can't be reharnessed, it can't be recovered, and so it's lost. When work is done by the system is using its own energy, and the energy flows outward to do work. That's work done by the system. Work done to the system is a little bit differently though, and some of you may have one of those old school bike pumps to pump up a bicycle tire. And if you pump this thing up and down 30, 40 times, and you touch this thing, the barrel of the bike pump, you might notice that the barrel is quite warm. It gets a little warm. And you might ask yourself, well, where did that come from? Where did that heat energy come from? Because the internal energy of the system has definitely been increased because it's got more energy than it had before. The barrel is hot, whereas it didn't used to be. And I think it may be fairly obvious to see that the energy came from outside the system and went into the system. It came from you. It came from your own body when you were, here's a small person that has large arms and is pushing on this bike pump. The energy came from inside your body, and you're using your energy to do work, and you're putting energy into this system, and that energy directly comes out in heating up the bike pump and in a couple other places. So this is work done to the system. When energy comes from, so if this is the system, energy comes from outside the system and goes in, that's work done on the system, and the energy of the system ends up increasing. So that's the difference between work done to the system and work done by the system. You need to know this equation when we talk about change in internal energy. Change in internal energy equals Q, which is the thermal energy added to or removed from the system, and then plus or minus W. I'll go over the plus or minus right now, but W is work. That's the work either done to the system or by the system. And we go to this table. We need to determine if the Q and the W are going to go into the equation as positive or negative. It's pretty easy to see when we talk about heat energy that if we're adding heat to the system, Q is going to be positive, because in that case the temperature and the internal energy will increase. And if we're cooling a system down, that means we're removing heat from the system. By the way, side note, I hope you realize that there's no such thing as cooling something down, because there's no such thing as cold. It's just the absence of heat. So instead of cooling down, we should really say we're removing heat from the system, which is what it says here. But that would be a negative Q, because the internal energy and the temperature of that system are going to decrease if we remove heat from the system. However, work is a little bit harder to understand. If work is done to the system, that means the energy comes from outside and it flows in, like the bike pump. That's going to be positive work, and the internal energy of the entire system will increase because, for instance, the bike pump got hot. But if work is done by the system, that means the system itself is using its own energy to do work, and the work will flow outward from the system. The energy flows outward, rather. That work is negative because the internal energy will tend to decrease. And that's the example of that is going out and running a mile around the track. All right, so this is how to determine if work is positive or negative, and now let's look at a sample problem related to that. Let's say a certain system has 400 joules of heat, and the system does 200 joules of work, and we want to know what the change in internal energy is. All right, well, first of all, we need to know what our variables are. If we're looking for the change in internal energy, obviously, we're going to use this equation. 400 joules of heat, that's our Q. Okay, that's how much heat we start with, and it says the system itself does 200 joules of work. So we need to know whether this work is positive or negative, and that's where we look back at our table and we ask ourselves, well, is work being done to the system or by the system? Well, in this case, the work is being done by the system. The system itself is doing the work, so our work must go into the equation as negative. So the system does 200 joules of work, and so we're going to plug in the numbers this way, 400 plus a negative 200, and you end up with a change in internal energy of 200 joules. In other words, simple terms, system has 400 joules of heat and it uses 200 joules of that energy to do some work. You end up with 200 at the end. That's the basic point in a nutshell. So that's the first law of thermodynamics, but the first law doesn't tell us what direction energy flows. It just tells us it's got to flow. It's got to go somewhere. The second law tells us what direction it goes. Heat will flow spontaneously from high to low. And the word spontaneously means it happens all on its own. I don't have to tell it to go. I don't have to add any energy. I don't have to prod it along. Heat automatically goes from high to low, which means if you put a hot object and a cold object next to each other and they're touching, heat will automatically flow from the hot one to the cold one. So the warm one will get cooler and the cool one will get warmer, and this happens naturally, spontaneously. I don't have to tell it to go. I don't have to push the on button. Happens automatically. Kind of like a waterfall. When you stand at the top of a waterfall, everybody knows water always flows downhill. That's a spontaneous action. It happens automatically. We don't have to get that to occur. We can get it to go the opposite direction. We can pump it up to the top of the hill, but we have to do some work. And this is where we're hitting on entropy. Entropy is a special term that just means the amount of disorder that's in a system. And any system, the entire universe as a fact, as a whole, the entire universe is a system. Any system will tend to move toward disorder, toward greater degrees of entropy, unless work is put into the system to change that. For instance, your bedroom. You might have noticed that if you don't take some effort to kind of clean up your bedroom, at the end of the day, at the end of the week, you might find that your bedroom is looking pretty bad. Those of you that keep a neat bedroom, you know that you've got to do some continuous work to keep it from getting dirty, right? And it's the same thing with the water that goes down the hill. If we want to go against the grain, if we want to get it back to the top of the hill, we have to do some work to do that. So everything is tending toward a state of disorder, toward a state of greater entropy, and to get it to go the opposite way, we have to do some work to do that. This slide basically says the same thing. Entropy is a measure of disorder. Disorder occurs because not all particles are moving at the same speed. It takes work to get a disordered system more organized, right? And something you need to know about thermodynamics is that if we add heat, the level of entropy is going to increase. Because generally, if we're adding heat, that means the temperature is increasing. And if the temperature is increasing, that means the kinetic energy of the molecules is increasing. Their motion is becoming more and more chaotic and random. So we have a greater degree of entropy with addition of heat. And likewise, if we're removing heat, we're decreasing the entropy. We're giving the molecules more order, more stability, less chaos. If there's no change in heat, entropy remains the same, obviously. And that brings us to the idea of a heat engine. Heat engines are important to understand, and I want you to use this part of your notes. In this large box, you can draw a diagram that looks like this. There's a large rectangle at the top that says TH, a large one rather, at the bottom that says TC. Okay, and what these are called, this is sometimes called the heat source. Sometimes it's called the high temperature reservoir. I'll have to go outside of the box a little bit. High temperature reservoir, the input heat, something to that effect. But the point is, if you have something that's hot up here, temperature, hot, that's what it stands for, hot temperature object and a cold temperature object, and if I connect the two of these things, the second law of thermodynamics says that heat is going to spontaneously flow in this direction, like a waterfall. It happens automatically. This is a natural process. It's a spontaneous process that just happens. Heat wants to go from a hot object into a cold object. Okay, and this TC down at the bottom is sometimes called the heat sink. Okay, because that's where the heat is going to, literally kind of like the sink where the water goes into. That's where the heat ultimately will flow into. This is sometimes called the cold reservoir. It's also sometimes you'll refer to it as where heat is rejected. Waste heat. All of those things apply to this bottom one down here. So heat flows this way. And just like a waterfall, sometimes they put hydroelectric plants on a waterfall. And what a hydroelectric plant does is it takes advantage of this natural flow of water to turn a big cogwheel that converts the kinetic energy of the water into mechanical energy of the wheel, and that ultimately gives us electricity. Well, this doesn't give us electricity necessarily, but from this natural flow of heat, we can use that flow, we can tap into that energy flow and get some work out of this engine. Okay, we can tap into this input heat. This is QH, the input thermal energy that's put into this heat engine. And this is QC down at the bottom, or QL. This is the output heat, the waste heat, something like that. And a really important equation that you need to know is this. QH equals QC plus W. Here's what that means. You have energy flowing in this direction. Some of this energy gets diverted off in this direction to do work, but not all of it. Some of it gets diverted off to do work, and some of it goes into this TC down here. In other words, it gets split, right? This is the useful part. This is what we want to get accomplished. This ends up being waste. We can't really recover this stuff. But to get this total amount, we know that the total amount of energy that I put in has to equal both the addition of both places where it was split. So it equals the QC plus the work that we get out of it. That's a very important equation that you need to know. These are both thermal energies that will be measured in joules, capital J. All right? So that's a heat engine. And again, heat engines, the definition of a heat engine is a device that converts thermal energy into mechanical energy. Because heat is put into the high temperature reservoir at the top, it'll automatically flow, because of the second law of thermodynamics, to the low temperature reservoir. So if you have two things at different temperatures, heat's going to flow from high to low, and we can tap into that heat in this heat engine to get net work out of the engine.